All right, well, let's go ahead and kick off chapter 9. So this is we have left the second half of the book. We're now into the third half. The third part of the book, and this is really starting to get into the tool builders section. So this is for for all of you folks that want to help me build a platform for immutable architectures. And so we're kicking things off with one of the most complicated and general purpose algorithms that goes into any of these immutable runtimes, and that's query inverses. So give you a little bit of background. My first implementation of an immutable runtime was correspondence, and that was in C#. And that actually compiles the factual modeling language into C# classes, which is really cool and something that I want to get back to. But it used a pretty simplistic technique for determining what has changed if a new fact arrives. And then the second runtime is Janaga, and that's the one that I'm currently maintaining. That's a JavaScript library written in TypeScript, and that one has a much richer query inversion algorithm. As I was writing the book, I started out, hey, let's just simply describe what a query inverse is and how it works. And so I started going through the Janaga implementation. And of course, this being a math book, I wanted to write proofs showing that this algorithm was correct, and it wasn't. So there were some edge cases in there that it just doesn't work in, and as it happened, I just, in my applications that I had built with Janaga, I hadn't run into those particular shapes, but the spirit of the algorithm is still correct. It still kind of does the general purpose thing, but then I just buckled down and said, okay, if I were to create a real query inverse, what would it look like? And so basically, chapter 9 is the evolution, the inference of an algorithm based on the requirements. So for those that would like a quick introduction to what it is what we're talking about here, a factual query is something that returns a set of facts, a set of immutable records, based on the relationship that those facts have with other facts, their predecessor relationships. So a query will typically, you start at one fact, and then it will typically look for the successors, the things that followed after that. So maybe the fact that you're starting with is let's say that it's a discussion forum. And so the successors are all the posts that people have made in that discussion forum. And so when somebody makes a new post, you want to update your user interface. You want to send that post to all the people that are interested in it. And in order to solve those problems, you need to figure out if somebody were running that query, would they see this fact? Would this fact affect the set that they return? And in order to answer that question, what we can do is invert the query. So we can start with the post, run the inverse, and say, well, this post is part of this discussion forum. So anybody running that query for this discussion forum is going to be interested in this post, and send it along. So that's a really simple starting point example. It starts to get kind of complicated when you start talking about having existential clauses. So somebody could post in a discussion forum, but then they could delete their post. So the deletion is another fact. And so expressing that deletion fact affects the query by removing the post from its result set. Of course, the post still exists. These are immutable records, but you can change the results of a query by adding new facts. And so query inverses start to get a little bit complicated when that happens. And so what I wanted to do here is start with those constraints, those requirements. A query inverse will give you all the starting points of a query that would be affected by this new fact. And then from that requirement, derive a correct algorithm. And to kind of spoil it for you, there are some cases in that algorithm where you just you can't do the thing that that would be the most expedient. You can't just take shortcuts and optimize. There are some times that it's just, well, you have to think, well, this might have been affected, so just rerun the query and see if anything really has changed. So that's the space in which query inverses live. So as we start the discussion, I want to start by focusing on pipelines. This was the first thing that I recognized the Janaga implementation was lacking. So in Janaga, a query inverse is another query. And so it's missing a whole bunch of other things you could express in a pipeline. But a pipeline is basically a whole bunch of queries all merged together. It's a set of steps that you can take from a starting point in order to run a query that kind of branches out into several different directions. So if we kind of just this is the sort of thing that sharing my screen would be quite useful for. Unfortunately, I have it open on a different machine that's not shareable. So maybe I'll start bringing it up on this other machine. We can do a screen share as well. And while I'm doing that, the first example that I showed is you're starting with a cart and you're looking for all of the order lines within that shopping cart. So you're doing a successor query. You're looking for successors. So the pipeline of that starts with a set of carts, which initially just contains one item. And then you run a successor step. And that's basically a select many in .NET. That's your apply step in a monad, and it's from everything in one set. Run this step and get the next set. So that next set is all of the successors of that cart. So while I'm pulling that up, was that that idea of having a set, run a step, and that produces another step set. Was that something that you found familiar, like from select many in .NET, or is that kind of a new way of thinking through things?
Michael, your video is flashing in and out all the time. On Discord, but on Twitch, no. Nelson, are you seeing the same thing?
I'm not on Twitch, but on the Discord server, you guys look fine. Just
Okay, then it must be.
Yeah, I don't notice anything.
Then it must be a problem on my side. Never mind. Okay, then I will just see you on Twitch and hear you on Discord because there is some delay in the sound on both. Never mind.
Yeah.
Michael,
Yeah.
I was when reading the chapter, I was just wondering: is this query inverses? Is that part of something more general? What I mean is, if, for example, SQL, the SQL language, is also working with sets, just as we are doing here with factual, or with historical modeling. Does that mean that also a query in SQL could be inversed?
I don't think so. I don't think that's an operation that you could apply in general. So yeah, in SQL, you do have your structural query language, the way that you can express the query, but then it gets converted into a query plan. So yeah, like in Microsoft T-SQL, you could view that query plan as a graph, and you can see all the different steps, taking inputs, performing some operation, producing an output. In Postgres, you could see a tree in text, where you're showing all of the steps as elements of the tree. But yeah, all of the query engines will do that sort of thing, where it's not executing the actual SQL that you typed in; it's turning that into a query plan. Now, I don't think that it's a general operation that all queries could be inverted, and I think that that's because a SQL query is a lot richer than a factual query. It allows a lot more degrees of freedom. And a factual query is deliberately constrained so that it does only what only what you're really supposed to do on the set of facts. So yeah, I'm trying to think of an example of a SQL query that could not be inverted, but yeah, I'm having a hard time thinking of a specific case. Well, in SQL, your where clause can express any condition of any of the columns. In factual, the equivalent of a where clause is really just your starting set. You can only you start at one particular fact, and then from there it's all joins. It's all successor and predecessor joins. So so you're very constrained in that you can't query based on like one field of a fact. You can't say, give me all the successors where the name of the post starts with capital T or whatever. So because of that constraint, that means that now you can perform operations like a query inverse, whereas thinking about what does a query inverse mean when there's a where clause based on columns, that becomes a lot trickier to think about. But yeah, SQL wasn't intended to be inverted. It's trying to solve a different problem. So yeah, I think with factual, we definitely wanted to solve the problem of how do you update the view and how do you collaborate with peers. And those are not problems that SQL was intended to solve. So I don't think it's an issue for it.
No, but I remember there is something in the SQL Server, like, is it SQL notification or something like that, where you have a query, and when something changes in your database that would influence the result of the query, it will warn you. I've actually never used it, but it's a little bit the same as what we do with historical modeling. But so I don't know whether it works with a kind of query inversion. I've no idea.
Yeah. Actually, yeah. So if we think through this, so the way that the correspondence query inversion worked was actually based on update controls. So that's why correspondence and update controls are so tightly linked. Is that as it queried, it would actually load all the facts that it was using into memory, and then it would take a dependency on the facts that it referenced. So now it loads a fact into memory, and now it says, okay, I need to walk your successors. Now, if a new successor fact was added that would have affected that, let me walk your successors, then that's how correspondence knew, oh, okay, this view needs to update because something has touched that set. So very memory intensive, not doing the query inverse, but still that means that theoretically it is possible for anything that has this idea of observing state and then continuing down the path based on what it observes. I would take that back. It is a general rule that anything can be inverted. So it's really just the dependency tracking algorithm.
Okay. Then it's a system that you explain in the Pluralsight course about assisticant.
Yes.
Okay.
Yes. It's just assisticant runs in memory, and so correspondence had to load everything in memory in order to do its thing. And query inversion doesn't necessarily need to run in memory. You can run the query inverse directly from the database.
Mm-hmm. Okay.
So let me do a quick share of this guy. Yeah. All right. So, I don't see it updating the screen. Okay, there it goes. Just had to scroll it. Wow. That's not going to be very useful, is it? Okay, well, what you're seeing, if I keep scrolling it, is we're starting with a set of carts. We're running a step to find the successors within that cart role. And let me stop that streaming there. And then that gives you back a set of order lines. So those are the order lines that have that cart as a predecessor. So very similar to in SQL Server, if you are running a query plan of you have a line that comes into a box like a nested loop in a SQL Server query plan. That line coming in is really a pipeline that's carrying in a whole bunch of rows. So it's carrying in a set. And then that nested loop runs over that set and then gives you a bunch of joined rows, a bunch of rows that have foreign key relationships with those. And then those child rows come out the other side, and then we feed on to other steps. So the idea of first turning a query into a pipeline, that was an important first step for me to start to generalize the query inversion algorithm. So if you write a query in Factual, what you're going to end up with is a linear sequence of steps. So some are going to be successor steps. Let's go down to our children. Some are going to be predecessor steps from the child go back up to the parent. Usually it's zigzag to go to a different parent. But so when you invert originally in Janaga, I was doing the naive thing of just flipping all of those steps. So if it was a predecessor step, then perform the successor step in the invert. But the thing that that I realized, and I realized this even while I was working on Janaga, is that inserting something in the middle can change your query results. So let's see if I can tweak this to make this work a little bit better. I'll find another example right here. Let's try to share this one. Okay, that seems to be more stable. All right, so this model that we're looking at right here, this is a model from like a point of sale system at a restaurant. So you've got people seated at tables within the restaurant, the server, the waiter, waitress walking around serving those tables. The server is assigned to a table. So the table is a historical fact. So table number 5 is a real thing. The server coming on online, Kayla. So she is now ready to serve some tables. So her manager needs to assign her to some tables. So the assignment is, Kayla, you're working table 5. So that's what this model represents. So you can see the solid arrows from assignment saying that those two, the table and the server, are predecessors. So if I were to write a query that said, hey, what server is currently assigned to this table? Then the query would start at the table, and then it would find all the successors, so showing me the assignment successor steps. And then from assignment, it would run the predecessor step. So it says, okay, what server is assigned to this, is associated with assignment. So that pipeline of 2 steps would give you the servers for the table. The thing is, if you just run the inverse, then you would say, okay, when a new server is hired, then let me go ahead and find their assignments, find the tables for that assignment, and those are the views that are updated. So if somebody is asking who's assigned to this table, then you would update that view. The problem is that that view also changes when the assignment is created. In fact, that's the more common case, is that the server has already been hired, the table already exists, but at this point, they've been assigned to that table, so now you need to update the query. So the pipeline captures not just end to end, but all the points in between. So so this intermediate step can affect the results of the query. And let me see if I've got a good example here. There we go. So kind of building out this this idea of the pipeline. We can see that I started with kind of this notation that makes it clear that you have sets at every step. So you start with, in this case, a set of order lines, and then you run a filter, and that filter gives you back a subset. It gives you back only the order lines for which this filter was true. And so to say whether the filter is true or not, it's all based on existential conditions. Does something exist? Does something not exist? So here we have a not exists based on excuse me, the step. I'm looking for a successor order line. So if there is no so from the order line, I'm taking a successor step along the order line's roll. So if there is no order that says, hey, this guy is one of my order lines, then that means that that this filter will let it pass. So this middle order line right here, if we take that successor step, we'll see, okay, this order points back to that order line. It's got a not exists clause on it, so that means it filters it out. So it only lets through the order lines for which an order does not exist. So
one question, Michael.
Yeah, go ahead.
So you're saying a pipeline gives you a sequence of steps. So how do you determine do you have to do filter first before not exist? Does it matter if we do not exist first? How do you know?
Yeah, so that all is based on turning the query into the pipeline. So, for example, here, this is the original factual query that we started with. So we're going to query for lines remaining in the cart C. So the query tells us to match order lines where the cart is equal to C. So that's just going to be our very first step. We are going to, starting with the cart C, we're going to match on order lines where the order line predecessor is C. So it's just, so that very first line tells us the first thing we do is take a successor step. Find all the successors of carts, all the successor order lines. Then the such that follows the match. So that means that we have to do the existential query next, and that's the filter. So the input to the filter is basically the output from that successor step we just did. So those are all the order lines. And then not exists is telling us the clause. So are we going to look for existence or lack of facts? So exists or not exists. And then this second where clause gives us the step that follows after that. So so now we're looking for orders where their predecessor is the order line. So we're doing a successor step from the order line to find the orders. So parsing the factual really gives us the order of the steps in the pipeline.
Gotcha. Thank you.
Yep. Welcome. So so at this point, I start to kind of abbreviate a little bit, and instead of showing you, this is an entire set of objects that are coming in, here we're saying, okay, we understand it's sets all the way down. So I'll just show you the kind of thing that's in the set. So we're starting with a set of carts, which always has just one thing in it. All factual queries start with one. So find the successors, and we find order lines. And then we filter where not exists a successor order. So basically this gives you all of the order lines that have not been put into an order yet. They're still in your shopping cart. That's the semantic meaning of this query. So the cool part about expressing the query like this is all of the edge cases and all of the side effects are already part of the query. So if I add something to my cart, then what I've done is I've just created an order line fact. And I said, this is now part of that cart. And so by doing so, it now shows up as part of this query. When I click the submit button and I say, okay, take all the order lines that are currently in this cart and place that order. That creates the order with all of these order lines as successors. I'm sorry, as predecessors. I was seeing the name of the step because it's stepping in that direction. So it creates that order with all of the order lines as predecessors, which then takes them out of this query because of that filter. So the side effects are built in. It's the job of the query inverse algorithm in order to execute those side effects. And so now if I'm running a query that shows me everything that's in my shopping cart and I click submit, that screen should update and all those items should disappear. I didn't have to write code to do that. Query inverse does that for me. So that's the problem that we're solving here, and pipelines are the very first step to solving that problem. So the affected set, we can see these are some of my hand-drawn diagrams before my daughter got a hold of them and made them look a lot better. So the affected set is the set of facts that are changed because of the new fact. So in this case, the query that we're running is for this table, who is assigned. When an assignment is created, what we can do is run the inverse and say, okay, this new assignment affects that table. So anybody querying that table, their view needs to update. But now what does the update need to be? The update needs to be that I now put this server into the result set. So that server is part of the affected set. So in general, you can think of the affected set as things that are being added to the set because of a query. The more general way of thinking about it is that it's things that are added, removed, things that you have to reevaluate. But that's the idea of the affected set.
I think back to what Jan said at the beginning, I believe that we can compare this to SQL materialized views where inserting new assignment will update this materialized view, but adding completely new server, not. Yeah? Something like that. Because this factual modeling language you invented, it's, as you said, a little bit limited to what SQL does, yes? Because there we have many more possibilities to filter based on properties, etc. And here we have exist and not exist. Yeah?
Right, exactly. Yeah, so
but
it
it's
is...
somehow similar, because we can just take tables from the SQL, create graph of those tables. If we limit somehow the SQL we write, we can go backwards and create such inverse, yes?
Yeah, I hadn't actually tried that before, but I think that you might be onto something. So
I have one question. Did you think about applying this historical modeling to graph databases? Because we are working with graphs all the time in here, not with relational databases, yeah?
Yes, yeah. And in fact, graph databases tend to have the operators built in that really let you build out these pipelines in a more efficient way than perhaps a SQL database. The whole friend of a friend type query, we're doing all sorts of these kinds of queries in Factual. I would say that just like SQL queries are richer than factual queries. They have more operators. So do graph queries. So if I'm not mistaken, in a graph database, you can express a query that can follow friend of a friend some arbitrary number of steps. Whereas if you were to express that in SQL, you would do a fixed number of joins. So like if you were doing an employee database in SQL. So here's your employee, they work for this manager. That manager is also an employee, which works for another manager. So you could write a query that says, I want to see your manager 3 levels up. And you would have to do 3 specific joins in SQL. I believe in a graph database, you can say, I want to see all of your managers. And it gets you your immediate manager, their manager, the manager above them. And so that is a really powerful query, which factual does not allow. It doesn't let you express just arbitrary numbers. You still have to be explicit about how many steps you want to take. But yeah, I think that if you had a graph database and you wanted to convert your factual query into a pipeline and then write that as a query, I think that a graph database would be able to execute that pretty well. Yeah, but I think
one thing that we need to remember is when we insert something that it's deleting data, we still need to think about this. Yes, in typical CRUD database, we delete something and that's all. And when we select a table, this row will not exist. And in here, we need to still remember that this deletion is actually an insert. Yeah?
Yep. And let's see if I can find a really good example here. Okay, so yeah, removing results. This is where we're going to start to get into those results. Yeah, let's go ahead and focus in on this one here. So the constraints that are built into historical modeling in general, factual in particular, are there in order to make sure that the systems that we can then implement on top of those constraints have some very interesting properties, that they are eventually consistent, that they allow a person using a node to act autonomously without having to wait for that node to talk to some other node. So these are the things that we're optimizing for by adopting now some constraints. One of the constraints being these objects are immutable. You can't change them. Another one being you can't delete them. They are an indelible part of history. But yet you want to represent deletions. So how do you do that? So here we've got a query. It's looking for the games that are currently in progress for a particular player. So starting with this player, match games where the games player is equal to P. So you can think of that as the game has a predecessor, which is the player. So that match is actually doing a successor join. So from the player, find the successor games along that role. And so you can see there's the name of the role, player. And so we're looking for the games that are successors of that player within that role. So that's all the games that the player has ever played. But you're only looking for the ones that are currently in progress. And so as soon as somebody wins the game, you don't want that to show up in the list anymore. So you can think of that as a delete, remove this from the list. So we want to filter. So filter always takes an object, a set of objects to a set of the same objects. It's just going to give you back a subset. So we're filtering the games where there does not exist a successor win. So not exists a win where the win game is G. So yeah, that's an example of how you'd represent a deletion in an immutable system. And so the way that you would then invert that is as soon as somebody wins a game, what queries do you have to affect? Well, you have to affect, go up to the predecessor, which game did they just win? And now go up to that game's predecessor players. So presumably there are 2 players in that game. So you have now affected both of those player queries. So those 2 people, starting with their player facts, searching for all the games in progress, as soon as the win occurs, that game in progress no longer appears in those results. And so this side of the dot shows you what you have to remove from those results. You remove the game itself. In some queries, as we start to get even more complicated here, we build up pretty complicated pipelines where the pipeline continues to the right there. So you've got more things happening that get you to the facts that you need to remove from the set. So yeah, in general, then coming back to what you were talking about, if you want to model a deletion, you will end up with a query inverse that looks very much like this, because you'll have a model that looks very much like this. But you will not, in an immutable architecture, you will not actually delete the record. So if you were writing these queries on a graph database, if you allowed the consumer of that graph database, the application that's using it, to truly delete records, then this stuff wouldn't work anymore. You wouldn't be able to prove that running an inverse will get you to the correct affected set. You'll miss out on the ideas that we're trying to solve for about autonomy and scalability, working and eventual consistency. Working on separate nodes. And so that kind of gets to the fundamental idea here, is that the reason for the constraints is to give us those capabilities. And so if we build on top of SQL or a graph database, we have to constrain the system that we're building on top of. So that was kind of a long answer, but I hope that addressed the core of the question.
But in this case, both game and win will update this query. Yes, because the inverse, as you mentioned, in this case, either win for existing game or adding new game to the table updates this query.
Yes, exactly. So yeah, you start with just one query. You start with just one simple statement of, this is what I want to appear on the user interface. And then from that, you derive all of the different pipelines of the things that could affect that query. So yep, you're right. In this case, you will end up with a pipeline that starts with the game, and you'll end up with a pipeline that starts with the win. The game pipeline will add the game to the results. The win pipeline will remove the game from the results. Now, what I love about this stuff, and what I think is so cool, is that as a human, I don't have to think about what happens when this thing occurs. So somewhere in the user interface, I've written this query, and I've populated that list over there. So I don't have to think about, oh, okay, checkmate, haha, you've won. oh, wait a minute, that means that I need to go over here and I need to notify this thing. So, throw that in a queue and subscribe to it over there, or raise an event and listen over there and notify property changed and all that mess. Don't worry about that at all. You've written that query and somebody has created a fact. That's all you need. You have expressed the intent, and this just makes it real. The other really cool thing about it, as we get into I guess this would be chapter 12, is query inverses are not just for updating views on your machine. It's also for who do you notify? Who else is interested in this this particular fact? So I've just moved a piece, I've checkmated, I've recorded that fact. Running this query inverse, I can see that okay, my win in this game has 2 players. Okay, that other player, they've talked to me in the past, and they've said, hey, anytime this pipeline changes, I want to be notified of those facts. And so I just say, oh, okay, you're interested in this win. Here you go. And I send that win along. So I know based on this inverse that they're interested in it. And when they receive it, they'll say, oh, here's a fact. I don't know why I care. But then run it through my inverses, and it says, oh, I care because that's going to affect this part of the user interface. And it does the update. So as a human developer, you get to just express your intent in terms of queries, and then the runtime picks up from that and shares things where they need to go, updates the user interface where it needs to be updated.
Michael, does that mean in the case, can you go back to that diagram that or that user interface that you've drawn yourself?
Yes. Somewhere up here.
It should be on page 294 in the final book.
Yeah, unfortunately, this is... There we go.
Yeah, there it is. So here we have a screen per server, and we see all the tables that are assigned to this server. Yeah. Imagine that this would just be a tab, so a screen, multiple tabs. In a restaurant, you have 20 servers, and every server has its own tab.
Mm-hmm.
Yeah. We go even a little bit further. It's not only the table number that you see, it's also the party that is seated.
Mm-hmm.
At a certain moment, there is a new party that comes in and that will be seated at a table. In that case, does that mean that normally for every tab, so you have a single tab per server, you have 20 servers, so 20 tabs.
Mm-hmm.
So you should run your query 20 times.
Hmm.
Yeah.
That's the...
In this case, there is a new seat party fact arriving.
Mm-hmm.
So the inverted query will generate one single set of servers, which contains all the servers, perhaps 5 servers, to which that table has been assigned.
Mm-hmm.
So that means instead of 5 servers that should rerun their query, now with one inverse query, you can notify them. And then with the forward part of that inverse query, you can just update their screen. Is that correct?
Yes. Except when you started, you were talking about, and so you have to run the query 5 times. That's one of the advantages of pipelines, is that that will allow the runtime to recognize that I'm running this query based on results of a previous one. So I can simply take that pipeline and append it to this pipeline. So now I've run the pipeline once, and I get back all the results of all those queries. So then I can then go through and put those results into the appropriate parts of the user interface.
So where traditionally you should run the full query, the forward query 5 times. But so now you replace it by one inverse query that notifies the 5 servers. And each of them will also get the forward part of the inverse query, the part on the right of the dot.
Yes, yeah, that's the other part of it.
To update their screen.
Right. And so for a query in which that part of the inverse is possible, and there are some cases in which it's not possible, and so we go into some of those edge cases, and if this happens, you have to give up and rerun the query. But if that part of the query is possible, then they just run their query from that point forward, so they know exactly what to add to their user interface, and it's not a complete refresh and rebuild.
So that means that this inverse query thing will also be very interesting in terms of computation, in cases where you have to notify a lot of people.
Yes, indeed.
Okay.
And as it turns out, most of the queries that that you'll end up using they produce pretty simple pipelines. The example pipeline that we were looking at is a very typical one. Successor with a filter for not exist successor. And so we already saw that inverse takes a pretty simple shape where you can say, these are the ones that are affected, and this is the affected set. And you don't have to go any further. You know that's deterministic. And so, in those cases, you just run the inverse, and you say, okay, those machines need to know, and here come the facts. They receive the facts, they run the inverse. That control needs to know, and here's the new item to add to the control. Yep.
So we should be able to build in a query inverter in the server itself. Now I'm meaning about, I'm talking about the Jinaga server, not the server of the restaurant.
Yes. Yes, exactly.
Okay.
Exactly. The immutable runtime knows how to run these inverses. So that's kind of what this chapter is a description of an algorithm that needs to be in an immutable runtime, not an algorithm that as a developer you need to really think about and write yourself. That said, as a developer, I look at query plans all the time. So this is kind of like, hey, if you're going to peer under the hood, take a look at the query plan. This is the kind of thing that you're going to see. So I think that this information is still going to be useful to the practitioner, but it is primarily for the tool builder, as the remaining chapters are.
It's quite amazing.
One quick question. So in order for this to be super useful, you will have to implement this runtime on every system, like, whether it's on the front end or back end, that needs, to query the historical models, right? You want it to be ubiquitous on all the platforms that you run on.
That is true, and we've got a lot of work cut out for us. So that's part of the reason that I switched when going from correspondence to Jinaga, switched from C# to JavaScript. It's like, okay, this is going to hit more of the platforms. Of course, now with Blazor and WebAssembly, C# is hitting all those same platforms now as well. So now is the time to switch back to. But I'll still. In fact, Jan and I were just talking about we're starting up the Jinaga.net project. So that is now on GitHub, living right alongside of Jinaga JS. And so that's when that's done, that's going to be 2 runtimes, and they will both implement query inversion. They'll be able to run queries. They'll be able to record new facts, and they'll be able to talk to the same backends. So so no matter what your backend is, these are your different client libraries that you'll be able to use to write your mobile apps, to write your web apps, to write your desktop apps, all talking to those backends.
Wonderful news for .NET developers.
Yeah.
So I thought that I read your book, and I think it's amazing, this mathematical background, etc. But on the other hand, I saw that you started 10 years ago or so, and from my friends, no one heard about historical modeling.
Yeah.
And that's a little bit shame, because when those tools will be ready, maybe to gain more attention to this historical modeling thing.
Mm-hmm. Yeah, I hope so. I think so. And yeah, I started historical modeling as an analysis technique, just trying to figure out what's going to happen when this person makes a decision. Okay, that person needs to learn about it, that kind of thing. And then realized, hey, I could actually write systems based on these rules. So for quite some time, I've just been writing my distributed systems using SQL, using .NET, using Node, but based on the principles of historical modeling. So like when I define a connection string for my SQL database, I will give that user 2 permissions. They can select, they can insert. They can't update, they can't delete. And then design the tables so that you just do your inserts, you have your foreign keys, you write your queries based on exists, not exists, based on these joins, and you get your answers. And so the patterns are still quite useful even without an immutable runtime. But then when I developed correspondence and then later Janaga, I started to really get the sense of I can express something very succinctly, and then it has the right behavior. So like in Janaga, you write a query and then project that query into some JavaScript view models, and then write some React to project those view models into a view. And now, okay, record a fact, and the view updates, and it does the right thing. And so I end up just writing very small pieces, and then things happen. And so I really am looking forward to taking these general purpose algorithms and general purpose runtimes and sharing them with everybody, finishing out the suite so that everybody can have those same experiences. But yeah, even before then, patterns are still useful. So I'm still building regular systems on top of those patterns without an immutable runtime, even today. That's one of the projects that I'm working on for a client, is yet another historical model.
It's nice to hear that it's production-ready knowledge.
Indeed. Well, I believe that is our time today. So next time we get together, we are diving into
SQL, I think.
Yeah, the SQL stuff. So. So yeah, that's actually a really good continuation of what we're doing here, because the pipeline that we come up with here can then be translated into a SQL query, and that is something that you could do manually. You could just kind of slog through the math of creating the pipeline, and then slog through the the math of translating that into SQL. But you could also kind of go from a factual query to a SQL query pretty directly as well. So so if you don't need to go through the query inversion process, you can still take that factual query, turn it into SQL, and that process isn't too mind-bending. But then, yeah, what you end up with is, like we were just talking about, a system that you write using the traditional runtimes, but yet follows these practices. And then as we get to the end of chapter 10, we realize we could actually write an application agnostic database, and so that gets us back into the general purpose runtimes. So that's going to be good stuff. So I hope that you will join me again next week.
Thank you so much.
Thank you.
Thank you, Michael.
Thank you very much. See you next week, Michael.
See you then.
Okay, bye-bye.
Bye.
Bye.